All right, well, we'll get started here. We've got students here. Thanks for coming, gang. And this is 102. 12th lecture, the 8th. It's the 6th week. Getting there, man. And this is intentionally kind of an open forum, and a few of the students talked about an assignment we're going to take a look at. So any questions you've got, wing them to me, and if you're not here, you're a distance learner, you can email me. I know it's not as good, but this is what we're dealing with. Let's take a quick look at the Moodle. Uh-oh, I didn't want to go there yet. And where we're at, and that might help remind you of the questions you got. So this is not week 3 and 4. Come on, dude. There. Week 5 and 6, bioenergy. Going clear back to, well, that's my old notes on boiling water. And you'll have a problem on boiling water and assignment 2. Similar to the one you had in 101, but a little bit different. Okay, there's summary 2, and that's not up yet for work. Or summary 2, have you done summary 2? Okay, you've already done that. Okay, good for you guys.
Yeah.
Okay. Yeah. Okay, and we've already talked that you folks have pretty knowledgeable about the guidelines for the summaries and the problem sets, and there's the assignment 2. And apologize, I had trouble getting the videos from last Thursday posted. I got it done yesterday late afternoon. And you were here, so you don't care, but you distance learners, if you don't know, they're out there. And brings us to week 6. And Dr. Layton said he's lectured about as much as he's through the lecture on bioenergy, and wanted me to just keep it open for student questions, go through particular tougher concepts, problem sets, and whatnot, if you'd like. So this group wants to start by looking at assignment 1. Is that where we're at? Problem set 1, which goes back up here to what, second or third week? Assignment 1, this will be a good test for this guy. I haven't looked at this. Oh, this is Brad's favorite. Yeah, this one's a pretty involved assignment. When you go to document this assignment, it's good to do it in a table. And it'll help you to do it in a table if you know Excel at all. Even if not, it'll help you because you can just move, like you go ding, 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 and get the calculations done. But a table will help you lay this out. As in, let's look at this first, as I recall, okay? First, let's look at this first problem in problem set 1. Express the amount of energy that the average human consumes metabolically. Okay, there's some key terms there. Per day in calories, little c, calories are the big guy, big C, remember the difference? Joules, megajoules, BTUs, therms, and kilowatt hours. Show your work using the methods given in lecture. So, one tip in how to do this is to make a table, and I'll go there just momentarily. It's not really a part of the solution. Shoot. There. So you got this first problem, number 1, metabolically or whatever it is. I didn't write it all out. And then you've got all the, what was it, calories, all the different units you're supposed to do it in. Big calorie, therm, and all that. Well, problem number 2, when you go to look at this, is asking something different, but it's all the same units. So showing your answer here in a table is most useful to the guy grading it, and it's also kind of lays it out for you to do. all right? Particularly if you don't excel. You got the same unit conversions taking you start with, let's say, the little guy and go to the big guy, calorie to calorie, the same with this number as you do this number, you know, X and Y, say. So in this cell, if it's 1,000, if you divide by 1,000 to go from calories to the big guy, you can just divide by 1,000 all the way through here once you get the metabolically one done. You got to have the first number though, okay? All right, so you kind of diverted there from you a little bit. So what does this ask us? Anybody know what the amount of energy the average human consumes metabolically? And look at this, it's per day, okay? Per day. Anybody know that from their readings?
Isn't it 10 megajoules in a day?
Well, let's look in the text. We're going to pause the recording a little bit while we look around the text for what might be applicable, and then when we get there. Yeah, this problem demands a starting point from our lecture and from our readings, and Zach said it well. You got to be in the ballpark on the starting point. You don't have to be exactly one way or the other. And to wit, here I started to throw down the makings of a table as a way to do this problem. And I don't know if you can read this very well. We got little calories, big calories, joule, megajoule, BTU, therm, kilowatt hour along the headings there, and in each problem, the first problem being the metabolic energy. Well, I think in lecture, I don't know if it's in the book anywhere really, humans metabolically per day use 2,200, 2,000 to 2,500 calories per day. And when we're talking human consumption, of course we're talking food calories, so we're talking the big guy, calorie to the capital C. And in your text, and Zach found what, page 7, Zach? We talk about the energy all of humanity uses throughout the world per year as 500 approximately, and I think I've seen numbers 502, 504 exajoules per year. We can go to these different places in this, what this problem asks, and further down the road in the problem we'll need to know how many people in the world there are, and there's around 7 billion, okay, as you're given. So let's go back to the problem. You show these side by side might be better, but not very good at that. So the first problem asks the amount of energy the average human consumes metabolically per day in calories. Well, little calories and big calories. We just looked at the commonality of a human eating 2,500 big calories per day. Well, you stick that number in your table right here. If I can get there. See if it'll work. Yeah, 2,500. From that, you can calculate all these. But you need to know the conversions. And your appendix is a great place, and your readings is a good place. Okay. Problem number 2 asks the amount of energy the average human consumes technologically per day. Okay, we just looked at what humanity does. We know the population. From that, we can calculate the amount of energy the average human consumes technologically in exajoules, but we need to convert from exajoules to all these other units, all right? And so forth down through these problems. The third problem asks for the amount of energy that humanity consumes metabolically per day and per year. So there's another row in your table that humanity consumes metabolically. So that he's wanting to know, okay, in the first problem we looked at what the average human does. Here we're looking at what all humanity does per day and per year. Fourth problem, amount of energy humanity consumes technologically per day and per year. Okay? So we're dealing with different time frames. Based on your answer from number 1 is the average metabolic energy consumption rate of the average human. Again, we know the number of people, we can calculate that. However, we're also asked to express the answer in watts and horsepower. So we'll need to go to those conversions. And based on the answer from number 4, with the technological energy consumption rate of humanity, well, we know what that is, we just looked at it. Express your answer again in watts and horsepower, so need your conversions. Okay? It's a kind of a ball problem. If students are getting on the wrong track, it's kind of a bear cat to grade because there's so many different animals in there, just on unit conversions. Okay, we got enough of that one done. Want to go anywhere further on that guy? Okay, but it's a good problem, and it's given to, we go through some of these problems or some of these parameters we look at. We're talking a power plant producing X amount of kilowatt hours per year or per day. And all of a sudden we're going and talking about megawatts of electricity, there you go, kilowatt hours per day, per year. And all of a sudden we're talking about how many megawatts the thing is capable of what's its capacity. So you're mixing units a lot. So this is a good problem relative to having you go through the mixing of units and understanding the differences. We good there? Let's see what time. Okay, anything from bioenergy you want questions about that is in the text? Anything in particular bother or confusion or comments? I'm going to give the class a few minutes here to ascertain what questions they may have on content, or whether or not we might want to go to assignment 2. And I've got a couple content items I want to take a quick look at here to see if they're worthwhile to go through. So we're going to take a little pause on you here. Yeah. Yes, we got a comment from a student, a question.
Somewhere in here, I think there's like the total incoming solar radiation
Yes.
from the sun.
Yes.
And I think it'd be cool to find out like what percentage of that is captured in chemical bonds versus what percentage is, soaked into the earth and radiation.
Yeah, I thought there was a figure in the text.
Yeah, I remember seeing one. I haven't.
Yeah, well, let's get there. Yes, we have a student that wants to review the, just as a matter of interest, what figure is that? And I'll get it on my, let's see if I can find that bugger. That goes clear back to autumn of 14, believe it or not, boys and girls. Excuse me, and we're doing bio. Come on.
Similar, but I want to find out like the total, like the total, instant radiation that hits the entire Earth. You could say in watts per joules per second or whatever.
No, that's
per year.
well, there's a table. In fact, do you have a problem number 1 of assignment 2 relates to, I think, a table that may be helpful to you. Right at the towards the beginning of this chapter on biofuels. Let's find it. I know Dr. Layton knows that number off the top of his head.
Well, the reason I started thinking about it is because of that Sharansky paper.
Mm-hmm.
It discusses a point where we just won't have any fossil fuels to use. So
Yeah.
what is the total maximum energy we can use from the sun? What is the maximum per capita energy consumption we could achieve? Which is a hard question to answer.
Is that covered in solar voltaics? Maybe not. Maybe it's on wind and solar, hydroelectricity. Well, let me pause this for a minute. That's a good question, and I've seen that number. I've heard Dr. Layton quote it, but I thought I've seen it in the text also,
Yeah.
related to maybe even wind and wave, because wind and waves indirectly come from solar. So, again, you distance learners, we're going to be looking something up here, and I don't want to have you guys wait for us to do that, but try to pause this. Yeah, we're looking to find how much energy in total from the sun reaches the Earth surface. Oh, I've seen that in the text. So we were just discussing total energy available. As one student put it here, Zach, how much energy is available from the sun once our fossil fuels run out? What's out there that we can tap into as we keep moving towards renewables, and we have to go somewhere to get it, because we're still going to want to light our homes at night and watch TV and do all the stuff we do. So this is figure 1.9 from the text, and it says intercepted solar radiation is around 5 million exajoules per year coming from the sun, okay? This isn't going to quite get to where you want to get to, but by difference we can kind of maybe ascertain what it is, right? Direct conversion to heat in the air, earth, and oceans, around half of it, 2.65 million exajoules per year. Solar radiation to space is a small amount, 1.67, well, it's not a small amount, 31%, 1.67. So that's worthless to us, right, on the Earth. What goes into the hydrological cycle, evaporation, precipitation, is about 1 million. That's worthwhile to us, because that causes the, we can do hydroelectric from it. Evaporation, precipitation help cause wind and waves. Photosynthesis is a small amount, 1,260 exajoules a year. So it looks like of the 5 million exajoules per year, about 2/3 of it is useful to us. Am I looking at that correctly? Yeah.
70%.
Yeah. About what's 70%? About 35. About 3.5. That look right? Maybe a little more than 3 now. About 4.
3.8.
Yeah. Yeah. About 3.8 million exajoules per year, and we just talked about humanity using over 500 exajoules per year. Wasn't that what it was? Yeah, technologically. 500. So really what's available out there to us is many, many times that. And I've seen Dr. Layton go through this. Now let's look at bioenergy and how that relates as an example. And this text, I believe, if I remember properly, and the lectures at the beginning of a section, for example, on hydroelectricity, or a section on wind, or a section on wave, talks about what's totally available out there. They think, looking at it this way, as in figure 1.9 is available for wind and wave, available for geothermal, available for these renewables as a percentage and then they look at what's being used now and what's technologically feasible to do in a very, very rough sense. But it's a lot. It's a lot more than we use, which is encouraging. Yeah, good point. So let's go to bioenergy. And this is a pretty interesting table. And I wanted it students got to look at. That's why I made it into part of this into a little bit of a problem and assignment 2. It's the first problem assignment 2. Look at page 119, table or box 4. Oh, even worse. Box 4.1. Okay, page 119. Hope I got this thing going. Let me look. Yeah. Let's get this garbage out of here. Oh, here I got this problem again. There. Okay. Hopefully I could write now. Sorry about this. Table 4.1, or box, excuse me. Page 119. What's this thing doing? It's look at a basic biomass data. And you got to know these are very, very rough estimates. But look at world energy comparisons, the next section down. And that relates to just what we were looking at with what's available for the sun. So the solar reaching the Earth, we figure, was about approximately 3.8, Shauna, million exajoules per year. Is that the number? Yeah. Sideways sun. Okay, but bioenergy, world energy comparisons. Get over here. There it is. We look at the rate of energy storage by land biomass. Land biomass is 2,400 exajoules per year, right? And he even gives you the 76 terawatts. That's the power. That's the rate, okay? Global primary energy consumption. Well, we just looked at that. There it is listed at 502. I thought I saw 500. We'll just look at that with problem 1. We got approximated at 500. 502 exajoules per year. I'm getting already writing these things sometimes, sorry. The biomass energy consumption, and you got to read, this confused me when I first got into it. This is the rate that we use biomass for energy now. 50 gigajoules per year. Exajoules per year. And food biomass energy consumption is 29. This is exactly what I laid out in problem number 1, assignment 2. wanted you to look at this data and find out, well, available on the Earth, there's 2,400 exajoules per year of biomass energy, okay? Not very much compared to that 3.8 million coming from the sun, but, and then there's a, earlier in the text it goes through that, where that energy goes. We use 500 exajoules per year of humanity. So there's a lot more available there than we're using, but that 2,400 isn't the total story. That's by problem at least too, if I remember right. You gotta subtract these two. We're using 50 now for energy, and we're using around 29. So we're using a total of around 80. We're using now for food and energy. So we've got left, still you got 2320, you got way more than 2,000 exajoule per year is available for bioenergy. Another, hey, now how much of that is technologically feasible? Yeah, there's a lot of algae out there that could be used for bioenergy, but it's how much of that, where's it at, how available is it, how expensive it is to process. A lot of trees out there, you're not going to, okay. Kind of got off, you got me on a good topic there, thank you. So you follow that? Yeah, it's not rocket science, but I think, again, taking a little harder look or a little more complete look at some of these tables can really tell you some stuff. And as you get through the course, as I stated, these technologies like wind, wave, solar, even tidal, early in the chapters they'll present numbers like this that compare what's out there and what's technologically feasible. And it's a lot. It's a lot. Okay? We just got to bring the cost down, don't we? Okay, any questions on that? Let me look and see how we're doing on the time thing here. That was good. Yeah, let's do it's a good time to pause it. What are we up here, 4:30?